So momentum. Here's where we're going to start. Imagine we have two massive objects. Okay, we'll call this M1. And we'll call this one M2. And this one is traveling in such a direction. And this one is traveling in this one's traveling in that direction. All right. Now we're talking massive objects, not just, we're not two boulders rolling past each other. We're talking like stars, okay, in this particular case. And in this particular case, these stars would have a force of attraction, right? We know from gravity that they're going to be attracted to each other, yeah? Okay, so this one is going to have this right here, which would be the force of M2 on the first one. And we would have that, which would be the force of the first one on the second. Yeah? Okay, now for intents and purposes, we have, or this constitutes our system. Okay, and there's nothing else around. There's nothing else going on here. Well, when I taught you guys about force, I lied to you. Well, I didn't so much lie to you as I didn't quite give you the whole truth. The way Newton described force wasn't so much the way we talked about force, and when an object has a force, we learned that force equals mass times our acceleration, right? But what's acceleration? Acceleration is really equal to what?
Mass times the gravity.
No, how do we come across acceleration? Acceleration's in units of meters per second squared, or what is? How do we define acceleration?
Change velocity.
Not just change in velocity. It's change in velocity with respect to. I mean, if we change our velocity, we go from 5 meters per second to 7 meters per second. We have a change of velocity of 2 meters per second, right? Positive 2. Acceleration is that 2 meters per second that occurs over a unit of time, right? So our acceleration is really equal to our change in velocity over our change in time. Yeah? Hopefully this rings a bell with you guys. Okay, so what's really going on here? This force, the force of 2-1, is going to change our velocity here, yeah? So we're going to have, so when we take the first object, we're going to have the force on this first object is going to be M1 times does that make sense? That it's going to it's going to be the change in the velocity 1 times the time. So that's going to be the force. Okay, so force 2-1 is going to be our first mass times our change of velocity or change in time. And our second one is going to be essentially the same thing. That it's going to be M2 Okay, or just the mass of the first one times the acceleration on the first one. And the mass on the second one times acceleration on the second one. Okay. But we know that these two, if we add them together, we know that F21, here, let me move this over here to the side. That these two, because they're in opposite directions, but they should be the same size, that if we add them together, we get 0, right? They're equal and opposite means that if you add them together, we're going to get 0. Yeah? Okay. So we're going to do a little bit of substitution here. And we're going to plug these things in for F21 and F12. So we're going to get M1 delta V1 over delta T plus M2 delta V2 over delta T, and they're going to equal 0. Well, these are both of the same amount of time, right? So let's factor that out here. Let's do M1 delta V1 plus M2 delta V2, and this whole thing is going to be delta T, and this equals 0. Well, if this plus this divided by time equals 0, what can you tell me about this up here? Or what's going on here? It got dark in here. Yeah.
Negative and positive.
They're negative and positive, but the sum together is going to be, okay, or let me put it a different way. Assuming that our masses are constant, okay, we can write this a different way. We can write this as delta M1 times V1 plus delta M2 times V2, right? If the mass is constant, we're just like multiplying a number in there, okay, and this whole thing equals 0 divided by delta T. This right here, that the change in this value plus the change in this value is going to equal 0, right? Right? Because the delta T, we could just multiply the delta T over. So we're going to go and then times delta T, and that'll become 0. Yeah? So what we get here is or the mass times the change in mass times velocity on the first object, because of Newton's second law, equals the change times the mass of velocity on the second object. Erase. There we go. Okay. Now, this only happens if we have. Okay, this only happens if this whole thing is an isolated system. Okay, that this is going to work. Now, this value that we have here, this M1 V1 and M2 V2, okay, this mass times velocity is called momentum. Okay. And the word definition of it is kind of difficult to explain. I like to think of it as an object's state of motion. but it sort of understates it because this also takes into account the mass of an object. So if you have two objects that are traveling at the same velocity, but one of them is more massive than the other, the more massive object will have more momentum. And this should fit with your guys' reality. You know, if you see someone on a bicycle, okay, or you're standing in the middle of the street and you have two things rushing towards you. You have someone on a bicycle rushing towards you, and you have someone in a semi-truck rushing towards you. Which one are you more afraid of? Okay, hopefully the semi-truck. Okay, or the super cool Tesla semi that's coming out, which I don't know if you guys paid attention to that, but it's an all-electric semi. That's yeah. Anyways, it's going to be a massive vehicle, and it will run you down, and where you actually might stand a chance with someone on a bicycle. Okay, might hurt a bit, but you won't die. Okay, because the bicycle actually has less momentum, and the truck has more momentum. Well, this right here is the change in momentum. Oh, and by the way, momentum has units of kilogram meter per second. Now we know that a newton is a kilogram meter per second squared, right? Well, there isn't really a unit for this. It's just a kilogram meter. I like to call it a mo. Hey mo. But that's just my term for it. I wish we could just call it a mo, but that would be a very English-centric term, and so we creatively call momentum. By the way, our value for it is p. That's our variable. I don't know why. I think it's because other letters were taken, okay, or were confusing. So we call this p for momentum. And this is either the kilogram meter per second, or we can call it a Newton second, and we'll show you why this is the value later. Okay, so these are our units of momentum. This is our momentum formula, P equals mv. And this value up here, okay, our change in momentum, delta P, which equals delta m times v, okay, is called impulse. And it actually has a letter J. Again, I don't know why. It's just called J. Okay, I think it's called J because I is already taken by electricity. I is the letter for current. So we use J for impulse. All right. So let's go back to this though. If these two objects are exerting a force on each other, but there's no other force acting on it, that the total change in momentum, that the change in momentum of one object plus the change in the momentum of the other object equals 0. Or that the total change in momentum equals 0, and that the total momentum is a constant, that the amount of momentum you start with is equal to the amount of momentum that you finish with. This is a fancy way of defining the law of conservation of momentum. LCM. This is the other LCM. Oh, sorry, we're off the page. This is the other LCM, not least common multiple, law of conservation of momentum. So we have some applications of this. If our two stars were to collide, or say they were black holes, you know, the big astronomical news over the last year is that we were actually able to witness the collision of black holes and predict the existence of gravitational waves coming from them. The whole idea of that gravity travels in waves, okay, was confirmed when we detected gravitational waves, which are phenomenally weak. That it took the collision of two black holes in order to detect them. But we did. Okay. And part of this whole process is that when they collided, that the momentum of one plus the momentum of the other remained constant the entire time. All right, so the way we write this out is if these two objects collide with a certain velocity, they each have their own velocity, they will equal actually I'm going to put primes next to these are little apostrophes. In other words, let's say they exchange mass. Okay. If they exchange some mass, then it's their new mass times their new velocity. But these two, the statement stays the same, that the amount of momentum that they have before a collision equals the amount of momentum they have after a collision. Or, what would a collision be in reverse? No, just instead of two things colliding, what would be in reverse? Yeah. Let's say it aloud. A separation. What if it happens violently? Okay. An explosion of some kind. So let's say you're launching the bomb's bursting in midair, right? From what song is that? Oh yeah, the national anthem. Okay, so we have the bombs bursting in air, right? Well, all of the pieces of the bombs bursting in air would follow the same idea. Okay, you take the total masses and all the velocities of all the pieces of the bomb. Okay, and you find their center of mass. Okay, and all of those momenta added together would equal the momentum of the bomb as it traveled along its path. Okay, even though it all exploded out and you have shrapnel going everywhere, the total momentum of all the pieces after the explosion is equal to the total momentum of all the pieces before the explosion. Yeah? Okay. So, to review, momentum equals mass times velocity. Momentum equals mass times velocity. Our change in momentum is called impulse. Okay, impulse, there's another formula for this. Our impulse is also equal to a force times the amount of time that force is applied. This equals your change in momentum. Or if you want to see it a different way, if change in momentum was delta m times v, well, we had up here delta m times, delta mv. Here's our delta mv divided by t. Okay, well, this is equal to force, right? We said over here that the force equals mass times velocity over time. Yeah? So Okay, so we defined this value by setting it equal to a force, right? Mass times velocity, right? Mass times acceleration. I just moved the delta to the other side. Well, if we multiply so now we have delta mv equals force times delta t. We have our impulse equaling force times our change in time. Okay. All right. So that is the overall starter on momentum and impulse. And that should be enough to get you guys started on your assignment for today.